Hello everyone, this is the third video in the series of introductory videos to topics in this course, recorded with the aim of providing a little bit more clarity to the students who have signed up for this course. Hope you have all watched the first 3 weeks of lectures and also attempted and turned in all your assignments. At this point, something I forgot to mention in my first introductory video is something that I forgot to mention in the previous video is that this time we are also planning to include additional tutorial sessions to help you with the assignments, okay, and you will start this has already started. You would have seen one video in week 3 which dealt with topics discussed in week 1, 2 and 3. And you will also see 3 more tutorials which will help you with problem solving and assimilating ideas from week in the weeks that are going to come up, the lectures that are going to come up in the following weeks. So week 4, what is in week 4? Let's see. I mentioned earlier that week 3 represent the third lecture of week 3 is when we transition from fundamentals of combustion to fundamentals of propulsion. Week 4 is completely propulsion related aspects, and particularly aspects related to solid propellant rockets and combustion of solid propellants. This is a topic that is discussed at some length in this course, and I mentioned in one of my earlier intro videos that it may appear a little odd that such an exotic topic, solid propellants, which is not so extensively discussed in traditional combustion or for that matter even propulsion courses. Why is it being so extensively discussed in this course? Is it just a bias because the instructors have done some extensive work in this area, and is that the reason why they want to discuss it in some detail? Yes, I would have to say yes, but it is not just that. There is a very interesting and specific reason why this needs an extensive discussion, in my opinion, and this is the reason. Okay. Before I go to the reason, let me quickly tell you what the topics are that we are going to discuss. As you can see, in week 4 there is a very specific phenomena called erosive burning that will be discussed. Then a very interesting phenomena called instability in solid rockets will be discussed, and what data from actual rocket firings can teach us is also something that is discussed in week 4. This is not something that you will find in a traditional propulsion course. In fact, I will go one step further and say perhaps the most reliable information we can get, or the understanding we can get about the behavior of a propulsion system, is from data taken from an actual system, an actual rocket firing, more so than in these difficult to study laboratory systems. The most reliable data comes from actual systems, and the analysis of that is going to give us the maximum understanding or insights. Okay, and in the following the analysis of pressure time traces, we will move into the question, or trying to answer the question of why modeling of solid propellant combustion processes is needed. Can it even be modeled? The answer is yes, and it is that model that is discussed in some detail in the next lectures, perhaps some of it spilled over into week 5 also. So week 4 and week 5 will be heavily solid propellant rocket related stuff, and now is the time for me to answer why such an exotic topic, not practiced by a large number of people, not studied by a large number of researchers, is discussed at great length. One answer which I think is important in my opinion is the following. There are very few exact theories in the field of combustion science. The conservation equations which we discussed, which was introduced in week 2 and week 3, the conservation equations have been known for a very long time, but the conservation equations are coupled nonlinear partial differential equations for which there is no general solution. Numerical solution is one way to go, and it is something that is extensively used with increasing computational power. We do a brute force solution of the conservation equations to understand how combustion happens in actual propulsion systems. Yes, that is one way to go, but an exact theory is always beautiful. An exact theory is something that will allow us to claim that yes, we do understand without having to do very detailed CFD calculations. We can say something accurate about what will happen when a particular experiment is done. So exact theories are always sought after, but there are not too many exact theories in combustion science. In fact, let me be brave and say that I do not know of any other exact theory other than the heterogeneous quasi one-dimensional model for a solid propellant combustion process that is discussed in this course. And it is this aspect, the appeal of an exact theory, is the reason why this is discussed in some detail in this course, and I would like the students who are taking this course to see this from that perspective. Do not see it as an unnecessary extensive discussion of an exotic topic, but as a sample of what an exact theory can do, what is the power of an exact theory, and that is what you should take away from this. Okay, and it gives me great pleasure to actually tell you that this theory, which a calculation procedure has been developed and implemented in converted into a MATLAB software, is being used by engineers in space agencies and DRDO laboratories to actually compute the outcomes of experiments with solid propellants before they do experiments. And it has been shown, not by me but by them, that the predictions of the theory, the predictions obtained even before the experiments were done, were in very good agreement with experimental data. And this is what I mean by an exact theory, where you can actually use a computational procedure, a calculation procedure, and get results, and then do experiments, and then see that they agree with each other. And this is an exact theory. This is the power of an exact theory. You may ask, what is the use of this? This is the use of it. Before this exact theory was available, propellant development would happen by trial and error, and the trials, or the what should be tried, is based on the intuitive understanding that developers have accumulated through years of experience. But now what this exact theory has done is to rationalize their intuition, brought to their attention several counterintuitive factors which were dismissed as anomalies in the past, and have now been explained using combustion theory, and now a new calculation procedure has been established which enables them to compute exactly what would happen when they make a particular propellant and burn it. Okay? And it is for this reason I think a detailed discussion of this topic is justified. Okay? So yes, the week will start with another again, I should mention this one appeal. One of the highlights of this week's lecture is the introduction of the exact theory called the heterogeneous quasi 1D model. The other highlight, which is something which is also not commonly found in combustion literature, is a beautiful scaling law. Okay, and how a phenomena which was thought to be complex, erosive burning is what I am referring to. Erosive burning, which you will see what it is when you listen to the lecture, something that was thought of as a complicated phenomena with very complex dependence on chemistry and kinetics, was found to just depend on fluid mechanics, or ideas, a simple idea from fluid mechanics as to how heat transfer occurs in a turbulent boundary layer with injection. Okay, and so the other highlight this week has, in fact I would say it's very heavily packed, and it has two important highlights of the course. One is an exact theory, other is a beautiful application of a scaling law explaining data from a wide variety of experiments done over decades with a very simple beautiful idea. And I would say that anybody who is interested in serious research in general and particularly in combustion science should be exposed to these kinds of powerful tools or powerful ways of thinking, and that I hope will be the takeaway for you from week 4 lecture. In fact, week 5 also I guess continues to discuss other aspects, extended aspects of the heterogeneous quasi-1D model and further ideas from the phenomena of instability or analysis of phenomena of instability in solid rockets. Okay, and that completes week 5. It also has a tutorial which covered everything from week 1 to week 5, but that will not be the case this year. We will have 1 or 2 tutorials before this tutorial. Okay, hope you will enjoy lectures of week 4 and week 5. Thank you very much. See you later.